Section: Introduction. In this section, we address a significant challenge in the responsible deployment of language models, LMs, how to identify and refuse unsafe prompts while still responding to safe ones. Organizations using LMs for public interaction have attempted to fine-tune these models with specialized datasets to enhance this capability. However, we find that the trained refusal behavior often does not generalize well to unsafe prompts that are different from the training data, adversarial, or involve multiple turns of conversation. We explore methods that can be applied during inference to improve LM safety. Specifically, we investigate feature steering, an unsupervised technique that modifies model activations during inference. This approach is inspired by advancements in understanding how models work. It involves identifying features that influence specific behaviors and using these features to guide the LM's responses in real time. To implement this steering for refusals, we train a sparse autoencoder, say, on the activations of the LM at a certain layer. The say helps us identify features that correlate with refusal behavior. By adjusting the activation values of these features, either increasing them to enhance the behavior or decreasing them to reduce it, we can steer the model's responses. We conduct our experiments using the Phi-3 mini model, identifying refusal-related features and optimizing their activation values to improve the model's safety. We measure the impact of this steering on safety by looking at refusal rates for unsafe prompts. We also assess potential trade-offs by examining refusal rates for safe prompts and overall performance on standard benchmarks. Our main findings include: 1. We can identify multiple features that mediate refusal using just one carefully crafted prompt. 2. Steering the Phi-3 mini model by enhancing refusal features increases refusal rates for unsafe prompts and improves resilience against complex multi-turn attacks. 3. However, feature steering can lead to increased over-refusal for safe prompts and a decline in performance on tasks measuring factual recall and reasoning. Notably, we observe that over-refusal does not seem to be a direct factor since Phi-3 mini does not refuse benchmark prompts, and similar performance declines occur even when steering unrelated features. While we can adjust the activation values to balance steering with overall performance, further research is needed to minimize the negative effects of feature steering on unrelated capabilities. Our work builds on existing studies of feature steering by examining a different problem context, feature identification methods, and benchmarks, leading us to similar conclusions about its effectiveness and potential drawbacks. We also discuss related work on steering techniques, which aim to modify LM behavior without needing to retrain the model. Recent studies have shown that feature steering can mitigate social biases but may come at the cost of performance. Our contributions extend this research by focusing on feature steering in multi-turn scenarios. In summary, we find that while feature steering shows promise as a safety mechanism, it remains an area that requires further exploration. We conclude with recommendations for future research directions. Section Summary. In this section, we address the challenge of ensuring language models, LMs, refuse unsafe prompts while maintaining performance on safe ones, exploring feature steering as a method to enhance LM safety by manipulating activations during inference. Our findings indicate that while feature steering can effectively increase refusal rates for unsafe prompts, it may also lead to over-refusal on safe prompts and regressions in overall performance, highlighting the need for careful tuning and further research. Section: Steering with Sparse Autoencoders. In this section, we discuss steering with Sparse Autoencoders, SAEs. We train SAEs to convert an input vector into a sparse representation and then decode it back to the original input with minimal loss. In terms of language model, LM, interpretability, the elements in the sparse vector represent activations of specific features that the LM uses when processing input. We can adjust these feature activations to either enhance or reduce their influence. The process can be summarized in a few steps. 1. Say training. We choose which part of the LM we want the say to reconstruct, such as the residual stream or attention layers. We then run inference on a large dataset, like general web text, training the SAE to encode the activations into a larger sparse vector and decode it back to the original dense activations. 2. Feature identification. We identify which parts of the sparse vector are activated by text related to the topic we want to steer. These parts indicate feature activations that can influence behavior when adjusted. 3. Feature clamping. We determine a value to set for specific entries in the sparse vector that likely affect the behavior we are interested in. This value is a hyperparameter that we need to fine-tune. The SAE then decodes this modified sparse vector and sends the dense reconstruction to the next component. Formally, the SAEs we study consist of an encoder and a decoder, each with their own parameters. The encoder is sometimes referred to as an activation function. The parameters are learned by minimizing the difference between the original and reconstructed inputs, while ensuring that the intermediate result is a sparse vector. In our context, the input vector is an LM activation vector, and the sparse representation is called the feature vector. We can adjust the influence of a target feature by clamping its value. We denote the modified feature vector with the clamped feature and pass it to the next component in the model. We may also include a countermeasure to address the inherent reconstruction loss. For our experimental setup, we use the rate of refusals to unsafe prompts as a measure of LM safety. We explore whether enhancing refusal features identified through SAEs can improve refusal rates for harmful prompts in both single and multi-turn conversations without affecting overall performance. We identify features for steering, determine optimal clamp values, and assess safety and performance across different scenarios. Further details on our benchmarks, feature selection, and evaluation metrics are provided in the appendix. Regarding model and SAE selection, we steer the Phi 3 mini model, which is one of the most capable LMs for its size and has a strong safety baseline due to extensive safety training. We use a TOP35 SAE trained on the residual stream after the 6th layer of PHI 3 mini, as it showed significantly lower training loss compared to later layers. The steered reconstruction and error terms are combined and sent to the next layer. We chose the TOP35 SAE for its simplicity and the user-friendly codebase from Eleuther AI. Our SAE was trained with specific parameters and an expansion factor, resulting in a total of 37 features, with more details available in the appendix. Section Summary. In this section, we describe the use of Sparse Autoencoders, SAEs, to manipulate feature activations in language models, LMs, for improved interpretability and safety. We outline the process of training SAEs to encode and decode LM activations, identifying key features for steering, and tuning their influence to enhance refusal rates for harmful prompts without sacrificing overall performance. Section: Evaluating Safety Through Refusal Rates. In this section, we evaluate safety through refusal rates using the WildGuard dataset, which contains various prompt response pairs related to different types of harm, such as privacy issues and misinformation. We focus on the human-reviewed synthetic instruction prompts from WildGuard's test set to analyze how often the language model, LM, refuses unsafe prompts compared to safe ones. WildGuard includes adversarial prompts that simulate hypothetical scenarios, allowing us to measure refusals from completely safe to more complex attempts to bypass safety measures. To assess refusal behavior, we utilize a Mistral 7B language model that has been fine-tuned for detecting refusals. Our analysis looks at two main metrics: the percentage of unsafe prompts that the LM correctly refuses and the percentage of safe prompts that it incorrectly refuses. Ideally, we want a higher rate of unsafe prompt refusals and a lower rate of safe prompt refusals. Next, we examine XS test, which tests LM refusal behavior with a variety of prompts, including safe ones that might trigger over-refusal due to their similarity to harmful content. For instance, a technical question about killing a Linux process could be misinterpreted as unsafe. Our goal is to adjust LM responses to reduce unnecessary refusals while ensuring it still rejects genuinely harmful prompts. We use a GPT-4o judge to determine if the LM refused a prompt. We also explore Crescendo, a framework for multi-turn adversarial attacks aimed at bypassing LM safety measures. In these studies, an adversarial agent engages the LM in a conversation that starts with harmless questions and gradually shifts to harmful prompts. If the adversary cannot get the LM to comply with harmful requests within 10 turns, the attack is considered unsuccessful. We analyze 5 harmful objectives, such as eliciting instructions for making a Molotov cocktail or generating misinformation about vaccines. We conduct numerous conversations on each topic, measuring success by the percentage of conversations where the adversary successfully prompts harmful behavior. Finally, we assess overall performance beyond safety benchmarks by examining the impact of feature-based steering on model performance. We use MMLU, a multiple-choice benchmark covering various subjects, to evaluate the LM's knowledge and reasoning skills. Additionally, we utilize truthful QA to check if the LM can avoid common misconceptions across different categories, measuring accuracy to see if feature steering influences its ability to provide truthful responses. Section Summary. In this section, we evaluate the safety of language models, LMs, using the WildGuard dataset to measure refusal rates for safe and unsafe prompts, while also assessing over-refusal through the XS test benchmark and analyzing multi-turn adversarial attacks with the Crescendo framework. Our goal is to understand how well LMs can refuse harmful requests while minimizing incorrect refusals of legitimate prompts, alongside evaluating their overall performance on established benchmarks like MMLU and Truthful QA. Section: GSM-8K COB 2021 Training VT. In this section, we discuss the GSM-8K benchmark, which includes 8,500 human-created grade school math problems. This benchmark is commonly used to assess the mathematical reasoning abilities of language models. We prompt PHI-3 Mini to respond in natural language and show its work, evaluating it with 8 examples that encourage a chain of thought. The GSM-8K accuracy allows us to examine the reasoning capabilities of the language model beyond the multiple-choice format used in other benchmarks. Next, we focus on feature identification. We explain that sparse activation encoders, SAEs, transform language model activations into high-dimensional sparse representations, where each entry indicates the strength of activation for specific features based on the input. A key challenge is understanding what concepts or behaviors these features represent. Typically, we analyze activation patterns across various inputs to create natural language explanations. However, recent research has pointed out a limitation. While these explanations can describe when features activate, they may not reliably predict how steering these features affects behavior. To tackle this, we take a targeted approach, which, although not suitable for large-scale analysis, meets our specific needs. We collect features that activate during a refusal response to a typical unsafe prompt, such as asking for a manual on making a Molotov cocktail. Using PHI-3 Mini in chat format with greedy decoding, we find fewer than 100 unique features that activate across at least 2 tokens in the refusal response. Given our smaller SAE architecture and the idea that refusal behavior is mainly driven by a limited set of features, we believe that important refusal-related features will be included in this set. After identifying candidate features from the Molotov cocktail refusal, we conduct a systematic evaluation to see which features effectively mediate refusal behavior. We perform a grid search using a random sample of 250 questions from WildGuard. This diverse set allows us to check if the features identified in the archetypal refusal apply to various harm categories. We hypothesize that features mediating refusal will show a significant increase in unsafe prompt refusals when amplified. To test this, we experiment with amplifying features by clamping their activations to a value of 12, while keeping other activations unchanged. We determine this value based on preliminary experiments that suggest clamping above 10 often leads to noticeable changes in responses. By analyzing how refusal rates change with these clamping values, we can identify features that consistently increase refusal behavior and find the optimal values that balance unsafe and safe prompt refusals. Our results indicate that feature 22373 has the strongest and most consistent link to increased unsafe prompt refusals. We observe that both unsafe and safe prompt refusals increase steadily as we raise the clamping values for feature 22373. For our main evaluations, we choose clamping values of 10 and 12. A value of 10 strikes a balance between enhancing unsafe prompt refusals and minimizing regressions in safe prompt refusals, making it suitable for balanced performance. In contrast, a value of 12 maximizes unsafe prompt refusals, which is ideal for scenarios prioritizing safety, albeit with a higher risk of inappropriate refusals. In our results, we find that steering improves safety. We present data showing how steering feature 22373 affects safety in both single and multi-turn conversations. In single-turn settings, amplifying feature 22373 increases PHI-3 Mini's refusal rate for unsafe prompts, including adversarial ones. We see a 43% increase in unsafe prompt refusals when we amplify to 10 and a 44% increase when amplified to 12. In the XS test, we do not see significant improvement since the unsteered PHI-3 Mini already refuses most unsafe prompts. Steering also enhances safety in Crescendo's more complex multi-turn setting, where clamping feature 22373 to 12 results in a lower attack success rate compared to clamping to 10. These findings suggest that improvements in safety through steering feature 22373 are consistent across different scenarios, including jailbreak attempts and various harm categories. It is encouraging that feature 22373, identified through a straightforward process, generalizes well across both single and multi-turn settings, leading to enhanced safety without altering the model's weights or prompts, which are typical methods for safety tuning. Section Summary. In this section, we evaluate the GSM-8K benchmark to assess the mathematical reasoning capabilities of language models, specifically focusing on PHI-3 Mini's performance in providing natural language answers. We identify and analyze key features that mediate refusal behavior in response to unsafe prompts, demonstrating that amplifying feature 22373 significantly increases refusal rates while maintaining a balance between safety and overall performance. Section. Feature steering increases over refusal. In this section, we examine how feature steering affects over refusal rates. Our findings indicate that while feature steering can enhance safety, it also leads to a notable increase in the number of refusals for safe prompts. This trend is evident across various clamp values. Although we expect some increase in refusals for safe prompts, the substantial rise suggests that boosting feature 22373 results in a disproportionate increase in safe prompt refusals compared to the gains in unsafe prompt refusals. We also explore how feature steering impacts factual recall and reasoning. While it makes sense that steering features related to refusals would increase safe prompt refusals, the drop in accuracy on benchmarks assessing PHI-3 Mini's factual recall and reasoning is less clear. We investigate whether this accuracy decline stems from over-refusal or incorrect answers, but we find no instances of over-refusal in the benchmarks we tested. Our analysis shows that all categories in the MMLU benchmarks experience regressions, and these regressions are not limited to sensitive topics that might trigger over-refusal. We notice that the steered model tends to choose response C more frequently than other options. We provide examples of errors in GSM-8K and truthful QA in the appendix, and further investigation is necessary to understand the reasons behind the accuracy drops. Next, we focus on steering feature 216, which relates to discussions of philosophy. We observe that amplifying this feature causes PHI-3 Mini to engage in discussions about philosophy even when it is irrelevant to the prompt. We identified this feature through a process similar to what we described earlier, where we pinpoint features linked to refusals of unsafe prompts. Since discussing philosophy does not directly relate to safety, this allows us to better assess whether performance regressions are due to steering safety features specifically or if they are a broader issue with feature steering. Our results indicate that steering feature 216 leads to greater accuracy regressions compared to steering refusal. We present examples showing instances of hallucination and poor instruction adherence, suggesting that the overall performance decline is not merely a trade-off between safety and capabilities but rather reflects limitations in our current feature steering approach. In our discussion, we highlight the growing importance of making targeted and dynamic updates to language models, LMs, as their capabilities expand. We have explored a specific method of feature steering to enhance the safety of LMs without altering their prompts or weights. Our results show that while feature steering can improve safety, it also comes with significant trade-offs, including increased inappropriate refusals and decreased performance on key benchmarks. These findings prompt us to consider future directions for leveraging feature steering to enhance LM safety. We also acknowledge limitations in our work, particularly regarding model and say selection. Although we demonstrate that feature steering can improve robustness, the range of possible steering hyperparameters remains largely unexplored. It is uncertain how well our results apply across different LM families and steering behaviors. Additionally, we used a relatively small say to simplify feature identification, but larger SAEs with more detailed features might better steer for safety without negatively impacting performance. A more nuanced approach to refusals, focusing on unsafe prompts without adverse effects, may require multiple features rather than amplifying a single one. We emphasize the need for rigorous ablation studies as a crucial direction for future research. Section Summary. In this section, we explore the trade-offs of feature steering in language models, noting that while it can enhance safety, it also leads to increased inappropriate refusals and decreased performance on factual recall and reasoning benchmarks. Our findings suggest that these regressions may not solely stem from steering safety features but could indicate broader limitations in the feature steering approach itself. Section: Comparisons to alternative techniques. In this section, we focus on our specific method of steering refusal using features identified through a specific analysis technique. We do not delve into the broader range of alternative methods, such as those found in prompting and vector steering research. However, we believe there is potential to improve safety by exploring a wider array of techniques discussed in the prompting, representation engineering, and mechanistic interpretability literature. We were surprised to find that feature steering negatively impacted the model's overall performance across various standard tests. The significant effects of increasing the weights on individual features indicate a lack of modularity in the features we examined. Our findings are purely observational and do not seek to explain the underlying reasons for this decline in unrelated tasks, even though the model's overall coherence was maintained. Understanding how enhanced features interact with naturally activated features could improve accuracy, making this a crucial area for future research. We also note that feature steering for refusal is not needed when the language model is given a safe prompt. Steering only when necessary can help avoid the performance regressions observed with constant steering. We can use existing prompt classifiers in many modern language model applications to signal when steering is needed. By combining feature steering with prompt classifiers, we may achieve better results than using either method alone. For instance, we could apply steering to prompts that are uncertain. In our initial study, we explore conditional steering alongside a prompt classifier, as detailed in the appendix. Another approach is to identify features that indicate unsafe prompts and only apply steering when those features are active. This steering could be improved by adjusting the weight of steering features based on the activation patterns of other safety-related features, including those specific to the prompt and the output. Practitioners with access to labeled training datasets could train this conditional steering mechanism using supervised machine learning to optimize feature selection and weighting based on both the model's internal states and the characteristics of the prompts. Future work in this area presents an opportunity to enhance current methods for feature identification and reduce the performance regressions caused by feature steering.